10 seconds. Good to go. All right. So welcome back, everyone, for our final session of the day on collaborative Earth system modeling in Canada. We have several presentations here to close out the session. Welcome back, everyone. And here we go. I heard myself talking because I did exactly what I wasn't supposed to. We're ready to go. Jake Eager-Nash will we'll start things off. I'll stop sharing, and Jake, please go ahead and share your screen. And then I'll give you a warning after 10 minutes have elapsed.
Okay, great. Thank you. So I'm Jake. I'm relatively new to UVic. I moved over to Canada and Victoria in the new year, and I'm working with Colin Goldblatt, Andrew Weaver, and Mike Levy from UVic, and Clarkson Abraham from CCCMA to sort of look at millennial timescale climate change in the Canadian Earth system model. So just a little bit of background. There's a model into comparison project called the Long Run MIP for sort of fully coupled Earth system models with at least 1,000 years of model simulation, looking at different sort of warming scenarios from abrupt forcings and linear forcings. And the idea is to run these long models to understand sort of equilibrium processes, to get better estimates for equilibrium climate sensitivity, and also just to understand long-term dynamics. So this panel just shows a range of the different models that are involved and some of their sort of operations, but I won't go into much detail on that here. So like I said, we're using CAN-ESM 5.1, and we're using both physical tunings, the P1 and P2. So P1 basically closely resembles CAN-ESM 5.0 and the sort of CMIP contribution, while P2 has been tuned to provide better ENSO variability and also has a lower climate sensitivity, which you can see on the right here with this sort of light blue line is P2 and the orange is P1. You can just see that the sort of lower climate sensitivity there for historical forcings and also for an abrupt 4 times CO2. And so we have a set of millennial scale simulations from 1,000 to 4,000 years that are still running at the moment, with some which have various degrees of abrupt forcing from for 2 times, 4 times, and also a half times CO2. So one of the first things to see, I suppose, is how does the temperature evolve in these simulations, and so just showing versus time. So we've got temperature anomaly, and then the black shows the pre-industrial run, and blue signifies cooler and is the half times CO2 run, while the orange is a doubling and a red is a quadrupling. And you can see that generally the pre-industrial stays pretty consistently at 0. It cools down a little bit towards the end of the simulation, but there's very little sort of fluctuation in temperature really. And you can also see that for the other simulations, you can see that all of them are sort of continuing to evolve still, even beyond 1,000 years. So P2, the P2 tuning is this sort of solid darker line, while the fainter line shows the P1 tuning, and you can see that the difference in sensitivity. Now we sort of look at how sort of close to equilibrium they are by looking at the sort of the net downward top of atmospheric radiative flux against the sort of temperature anomaly. So the dashed lines here show the first sort of like the classic sort of fit for the first 150 years just to show what sort of like the traditional estimates for equilibrium sensitivity are. The solid line just shows the decadal average and the progression there. And you can see that only like the half-time CO2 simulations are pretty close to equilibrium, while the other ones have still got a fair way to go. And from these, we can sort of look at what the sort of the warming per doubling is for each of these simulations. And you can see that the sort of the cooling from the halving is higher than the effects of the doublings. And this is maybe because of the high climate sensitivity of the model and the sort of high ice extent we end up getting. While we also see that a quadrupling of CO2 has a larger warming than a doubling, which is sort of expected. But these are just taken from estimates from the sort of the end of the run, but there's still a bit of evolution in them, so these might change a bit still as the model goes further and closer to equilibrium. In terms of the ocean circulation, just to give sort of a wide sort of range of things what's going on in the model. So this shows now the evolution of the AMOC and the maximum in the AMOC. So like generally, those things to note are that the abrupt 2 times we see an increase in the AMOC overall. AMOC sort of like increases slightly by about a sphere drop or so, but nothing, not a huge increase. While halving CO2, we see almost a collapse in the AMOC, which doesn't seem to show signs of recovery. Some other models show sort of more significant recoveries, especially in like the abrupt 4 times case, but we generally just see a decline in the AMOC followed by sort of somewhat recovery, but not reaching the sort of normal values even after a few thousand years. And we're still running these out for longer to see if anything else changes, but that's what we see there. We've also got some similar sort of plots for Antarctic bottom water formation, but I don't have that here, but I can show that at the end if anyone has any questions about that. And then I want to sort of talk about the cloud evolution in these. So, and particularly to start with the long wave cloud radiative effect. So the cloud radiative effect is the difference between the all sky and clear sky radiative fluxes at the top of the atmosphere. So it's looking at how much radiation does cloud absorb in the different sort of, radiation types. So in terms of long wave cloud radiative effect, we see that generally this follows with temperature for both the different tunings. We see that the warmer simulations with higher CO2 have an increase in long wave cloud radiative effect, which indicates sort of like warming associated with clouds with long wave fluxes. And and these fit quite nicely with sort of temperature. So if we compare the temperature anomaly for these simulations with the feedback parameter with the cloud radiative effect, we can see the equilibrium sort of, or like the close to equilibrium simulations in the dots, and then also an average from 120 to 150 years in the squares, and we can just see that these generally fit on a fairly nice like linear fit with temperature anomaly. And you can, so there perhaps is predictability in what your equilibrium cloud radiative effect is compared to like earlier in the simulation, that we can sort of gauge from this sort of linear fit. However, this is quite different in the shortwave case. So again, this is the shortwave cloud radiative effect now and the evolution with time. Now, if we think about the P2 case, which is the sort of darker lines, we see that increasing CO2 leads to a decrease in shortwave cloud radiative effect, which is sort of like a net cooling effect. And then, and similarly, when you decrease CO2, you get an increase in shortwave cloud radiative effect. However, it's quite different in the P1 tuning. we see the abrupt 2 times case. It starts sort of going positive, and it's very close to 0. It goes positive, and then it sort of sinks negative again. We see that both the abrupt 0.5 forcing case and the abrupt 4 times case both have positive values that are fairly similar. And so again, when we look at this sort of plot looking at how this compares to the temperature anomaly, the P2 case sort of looks fairly well behaved, you can see a clear sort of trend. Whereas the P1 case, perhaps like predictability of shortwave cloud radiative effect is harder from earlier points in the simulation, and there's less of a clear pattern between the different cases.
5 minutes.
Okay, thank you. And then if we look at the cloud evolution as a whole, so the sum of the shortwave and longwave cloud radiative effects, we see that generally the net cloud radiative effect is they cancel each other out and they come to somewhere near or not too far from 0. However, you see that in the P1 case, the abrupt 4 times forcing, there's quite like this sort of outline case where cloud radiative effect is quite strongly positive, because we had both the shortwave and long wave ended up being positive. So again, there's you can sort of see that the P1 case sort of has this quite extreme change in cloud radiative effect for an abrupt 4 times, especially compared to the P2 case. So in summary, we're still sort of trying to understand how CAN-ESM sort of is evolving, and it continues. We can see that it clearly continues to evolve beyond 1,000 years. Even it's still evolving at 3,000 to 4,000 years, and we want to continue to sort of try and, well, what the next sort of steps are for this is to understand what timescales are for reaching equilibrium, like how which parameters or which outputs are being driven by what sort of timescales, and also how do the clouds continue to evolve on these timescales. We sort of saw that there's some level of potential predictability from earlier in the timescales. So for earlier in the simulation, but I think there's still quite a lot to unpack in terms of how those are evolving. And these longer runs are also really important to provide understanding of low frequency sort of climate, low frequency events in terms of climate extremes. So that's something that we want to apply this model to in the future. But thank you, and please feel free to reach out to me like here or via email. Thank you.
Thank you, Jake. I don't see any questions in the Q&A. I don't know if there's some in the chat. Just checking here. So one of the things that's striking about CAN-ESM is that some statistics look quite noisy, but the global mean temperature variability seems to be really small. And I was wondering if you had a chance to look at look at the temperature record for the past 100 years or so, and compare what you see in terms of interannual variability in that record to what you see in the model.
Well, that's a good question. I've not compared it to the historical data yet. Part of the smoothness might be because there's a decadal average on the data. It's a decadal average. Okay. So okay. That sort of smoothed it out.
Okay, that would definitely.
There is a lot more variability in the monthly data and stuff. So.
Yeah, actually, we have time for one more question. So, hi, Jake. I may have misread your plot. This is Christian Seiler, I think. I may have misread your plot, but if I saw your figure correctly, both 0.5 times and 2 times CO2 caused an AMOC collapse. Correct? How come?
So the way that they sort of have opposite. So when you warm, there's like this initial transient behavior where you have a decline in AMOC, and that's fairly well expected for warming cases. And you see the half-time case, we see an increase and then a decline, and that's sort of associated with sort of like behaviors or changes in, like, I think, salinity initially, and you sort of you then sort of recover to a new state. So they have opposite effects, but long term the abrupt 0.5 sort of stays declines permanently, but the sort of the abrupt 4 times recovers. If that's
okay. So that's interesting though that you're getting. It is. I mean, after a couple hundred years, they're both reductions in the AMOC. So that's kind of interesting that somehow the model is in that sweet spot that of the strongest AMOC. Okay, good. Well, let's move on then. Thanks a lot. And next we will have Noah Stanton. So Noah, please go ahead and share your screen.
Okay, will do.
I'll give you a warning at 5 minutes.
Sounds good. Okay, I think it should be showing right now.
Yep.
Okay, then I'll get started. Hello, everyone. I'm Noah Stanton, a second-year PhD candidate under the supervision of Dr. Neil Tandon at York University. Excuse my voice. I lost my voice over the weekend, so if you can't hear anything I say, I'll just chime in and I'll repeat myself. So I'm just going to briefly summarize our published results on VOC impacts in pre-industrial climate. And this will be I'll just briefly go through the conclusions of that paper. And it will lead into the motivation of my current work that I'm doing on my PhD to assess the effective radiative forcing of this VOC chemistry in the Community Earth System Model version 2, as well as doing some more robust pre-industrial ensemble experiments. We've also begun to apply the same methodology in modern control runs with some ensemble experiments. So let's just start with a brief motivation for this work. Figure 1 is the assessed contributions to observed warming in 2010-2019 relative to an 1850 to 1900 climate. We can see a number of different chemical and aerosol species that contributed to warming and cooling over this period of time. Volatile organic compounds can be seen to contribute to warming, although once these VOCs react with oxidants in the atmosphere, they contribute to secondary organic aerosol, which is a subset of organic carbon. This organic carbon's assessed contribution resulted in cooling for this period of time, albeit with a large uncertainty that partially straddles the zero line. So these VOC to aerosol conversions include a myriad of reactions which have nonlinear effects on climate. So CSM2 WACM6 implements an increased number of these VOC to aerosol reactions. So we wanted to assess the impacts of this increased complexity on climate. So why don't we take a look at the methodology for this published work that we have. Figure 2 shows the 7 model components and coupler of CSM2, and its detailed chemistry climate interactions that are in WACM can also be seen in Figure 3. The component of interest for us, as I just had said, is the whole atmosphere community climate model version 6. Main differences between the two cases in this analysis, our cases being MACTL and WACTL, are outlined in Table 1. WACTL has detailed atmospheric chemistry with 231 resolved species and interactive VOC emissions used in Megan version 2, and VOC oxidation using the 1D volatile basis set. MACTL has a simplified SOA scheme, the SOAG scheme, in which precursor VOCs are assumed to have a fixed mass yield and then are emitted into the model as primary aerosol particles. These cases were run for over 250 years with the data for this paper being used from year 40 to year 250. External forcings and emissions were fixed to, they were cyclical 1850 emissions, so 12-month cyclical emissions over and over and over again. And then the significant differences of WACTL minus MACTL were identified. For brevity, again, I'm just going to focus on the conclusions of this work as it shows the motivation for the current work that I'm doing. If you want details of these results, though, the published paper information will be at the bottom of the next short conclusion slide for this work. So the difference, the WACTL minus the MACTL, resulted in about a -4 to 4 Kelvin regional difference in surface temperature. These differences, though, largely canceled out in the global mean surface temperature. The main driver of the chemical differences between these two cases in this analysis are obviously these VOC reactions. It resulted in less conversion of SO2 to sulfate in the tropics, which counteracted the tropospheric cooling that we saw elsewhere. This work has been published in ACP. So, as I had to clearly really just brush over these results, I really highly encourage you to check out the DOI link at the bottom of this slide. But this work brought up a number of questions. How are changes in the aerosol budget impacting cloud formation? How will modern human emissions impact these results? And can we assess the effective radiative forcing of this VOC chemistry? And also, additionally, can we make this analysis more robust? So to answer some of these questions, we started some fixed SST runs in 1850 conditions as well as in 2000s conditions. And we additionally started some ensemble runs to answer some of these questions. So one of the critiques of Stanton and Tandon 2023 was that we could not precisely assess the effective radiative forcing or ERF of tropospheric VOC chemistry, as we were using prognostic oceans in both of our cases, which leads to too much noise. So we decided to run fixed sea surface temperature experiments to assess the impact of this VOC chemistry in both 1850 climate and 2000s climate. So what is ERF? I mean, I'm sure most people here know what that is, but we can think of it as the energy imbalance imparted to a climate system by a particular perturbation. In our case, this perturbation was the tropospheric VOC chemistry. We have followed the Forster et al. 2016 fixed SST approach to measure ERF. In our case, the control simulations are the middle atmosphere chemistry cases, with the perturbed cases being the whole atmosphere chemistry cases, which have this VOC chemistry. We first calculated net radiation for each case, then took the cosine weighted global mean of net radiation, which ends up being a time series of yearly output, which then you take a rolling average of that difference between the perturbed case and the control. So figure 6 shows that the output from this calculation. And you can see in 1850 climate, the inclusion of this VOC chemistry resulted in about a 0.5 watts per meter squared ERF, and that crosses the zero line to become negative 0.0 watts per meter squared in 2000. So for the 1850 case, though, this is a little puzzling compared to our Stanton and Tandon 2023 results. So we wanted to revisit that work with a more robust ensemble setup. So yeah, I guess the question is, what was puzzling? So in our in the Stanton and Tandon paper, we saw that the GMST started as a positive difference, but in the integration period that we used in the paper, from year 40 to 250, it became slightly negative, albeit not significant. But the FSST ERF results suggest a slight warming of the climate system in 1850 due to the inclusion of this VOC chemistry. We suspect cloud changes between the two integration periods, year 1 to year 40, compared to year 40 to 250, may be leading to the sign change. But the other hypothesis is it may have been due to the initialization of our WCTL case. So to address both of these hypotheses, we have started looking into different integration periods, with some of those results being shown in figure 7A and B. And we also started matched initial conditions ensemble runs of the WACTL configuration. Figure 7A shows the net CRE differences between the first member of the ensemble comparison with prognostic ocean, and then figure 7B shows the net CRE differences with the fixed SST comparisons that we're doing. We can see a qualitative match between the two plots, but notable differences around the equatorial East Pacific and the Pacific west of Hawaii. This net CRE response is in the prognostic ocean setup, changes over different integration periods. So we suspect that sign change may arise due to cloud changes, but again, we've started ensemble experiments to really make that initial analysis more robust. So we also wanted to see if we saw that same transient response with these matched initial conditions ensemble runs. And so to better isolate that response, we started these ensemble experiments directly initialized from the scientifically validated MACTL case. There's generally two ways to set up ensembles, either a micro perturbation setup or a macro perturbation setup. We went with the latter, as we wanted larger differences in the initial ocean state. Figure 8 is a simple schematic just to show how we branched off our ensemble members from this MACTL case. this is a far more robust setup than Stanton and Tandon 2023, so we can be far more confident in the output. And as this experiment really just started, Figure 9 just shows some sample output of the GMST for the first two members of this ensemble. Whoops. And yep, the other ensemble experiment that we have set up is in 2000s conditions. In Figure 6, the Figure 6 that show the ERF results does show a dramatic sign change from 1850 to 2000s, and due to the inclusion of this VOC chemistry, and obviously changes in land emissions over that time. So we wanted to assess how this sign change in ERF realizes in the fully coupled setup with a prognostic ocean. Learning from my previous work, I've started a control simulation using the middle atmosphere configuration initialized with 2000 cyclical emissions. Figure 10 shows the GMST of this case, the M2000s case, and we can see a long adjustment period due to the inclusion of this of modern human emissions and modern CO2 levels. The curve fit is more of an eyeball to see when we'll reach that more ergodic state, but really, when the drift is at an acceptable rate. And it looks like it should be around 75 to about 200 more years of output. Once we reach that state, I'll initialize the 13 members in that WACTL case to start an ensemble run in the 2000s run.
You have about 4 minutes left. Noah.
Perfect. Thanks, Paul. We do expect substantial differences, as many important chemical species have been significantly perturbed since 1850, SO2 being one example. So I will just finish the presentation in a weird spot on reference slides, as these experiments are still ongoing, so the conclusions are really still being assessed at the moment. My email and my supervisor's email are attached below. So please reach out to us if you have any questions about our work. The basis of much of this work does stem from Stanton and Tandon 2023. So I really highly encourage you to take a read of that paper. The link can be seen in the bolded second, it's the bolded second last entry on this reference slide. But thank you very much for listening.
Okay, thanks a lot, Noah. Let me just check if there are any questions in the chat or Q&A. I don't see any. I'll just ask you quickly whether you could just help me out here, because it looks to me like a lot of the methods you're using for assessing sensitivity to VOC emissions is actually just kind of more general, like how the system responds to short-lived climate forcers. So do you see yourself like doing more work with like sulfate precursors, or like other types of aerosol precursors? Like what makes this work sort of it's a kind of naive question, but what makes this work like special to VOC to VOC formation of secondary organic aerosols? Are you picking up those kind of feedbacks in particular, or is it more general?
So some of the results that I weren't able to show was the SOA results and the OH results. And so
I see, okay.
we really do focus in on this VOC to SOA interaction, because it's probably the simpler way to start asking the question. But you're right. I mean, what's actually there are more aerosols than just SOA being impacted by changing this VOC chemistry.
Right.
And so some of the details are provided in that paper, but yeah, it's there's definitely a lot more being impacted than just the SOA system. So.
Okay, thanks. Now, I just noticed that the schedule is a little funny on the slide I showed initially, because it shows actually there's a gap now, or there should have been a gap, and because of one of the talks that was omitted. So so we're just going to plow ahead, and so 4:25 local time, which is 1:25 Pacific, would be actually the time that was actually on the slide for Noah's presentation. I propose we just keep going, and so we're going to do Erica and then Sylvie and Jason, and then when we end early, then we can kind of go into a discussion period. So everybody, please feel free to go ahead and keep asking questions in the Q&A. In the meantime, Erica, I'd like you to share your screen and you can get started.
Is that working?
Almost. Just a sec. I can see it trying.
Oh, how about this?
There it goes. Yep, it's good. It was just there was a lag.
Perfect. Okay.
Okay. Yep.
So I can go?
Yeah. Go ahead.
Okay, great. Thanks, Paul and Clint, for organizing. My name's Erica Rosenblum. I'm at the University of Toronto, and today I'm going to share some work that's been led by my collaborators, Robert Faber and Noémie Planette at McGill University. So this work has been focused on looking at upper ocean heat content storage in the Canada Basin. And one of the main results we found is that there seems to be some biases in that upper ocean heat storage related to how Pacific water is simulated in the models. Okay, so first I'll just start with a little bit of motivation. So as an example, this all comes back to what we saw in a previous study from salinity. So this is showing observed salinity with depth in both the observations and the models on the bottom. We have observations from 1975 in blue and 2006 to 2012 in red. And then the models, this is showing an ensemble basin mean from 1970 in black to 2020 in red, where each line is indicating 1 year. And as you can see in the 1970s, the models are doing pretty good, but it really fails to capture more recent observations that show much fresher surface layer and more stratified profile. And it turns out that this model bias, it's been seen across the CMIP3, CMIP5, and CMIP6 models, and also just the components looking at ice ocean models, the fully coupled models, and the high resolution models. And so because we're in the polar oceans, the salt really matters because it controls the density. And so that's impacting the vertical transfer of heat, nutrients, and ultimately sea ice evolution. And so there we go. Our question was, well, if this bias is existing across all models, how is this possibly impacting the upper ocean heat storage in CMIP6? Okay, and so now I'll back up a little bit because who cares about the Canada Basin? So first, where is it? It's just over here in this Beaufort Gyre region, and it's very close to where the Pacific waters enter to the Arctic Ocean. So this is a major source of heat. There's warm, salty water entering and subducting below the cool, fresh surface waters, and these waters have been shown to be warming over the last few decades. It's also a region of rapid sea ice retreat, as shown here. This is showing sea ice coverage change per decade. And so with the sea ice disappearing, that means there's more sunlight that can warm the upper ocean. And so we're also seeing warming surface water over the last few decades as well. And both of these sources of heat, they're right up at the top 100 meters, meaning they can influence the sea ice evolution. And today we're mostly going to be talking about this in terms of how the signatures that show up in temperature profiles. So this is a nice example of that. This is showing potential temperature is a function of depth for 2006 and 2020. And in 2020, you see this really pronounced because of all the warming, and you see these two little bumps that are indicative of these two sources of warming. The shallower bump just here, which is often called the near surface temperature maximum, or NSTM for short, and then this larger bump that's indicative of Pacific water inflowing and subducting below those cool, fresh layers. Okay, so just as a starting point, we wanted to ask, well, how well is the upper ocean heat content simulated in the models? So this is showing actually the upper ocean heat content as a function of depth, but instead of showing it for joules, we're showing it in terms of the amount of ice that heat would melt were to be brought to the surface from these different layers. So in gray, we're seeing all of the models from CMIP6, and then I'm going to highlight 3 that we're mostly going to talk about today. CESM2 in red, which really struggles with this. Aura5, which is a reanalysis product, which I'll loosely refer to as the observations, and then ECR3, which does a much better job. But overall, we find that 33 of the 35 simulations simulate less heat content in the top 100 meters compared to the observations. And then in September, we see something similar, though it looks a little bit better, but we find that of about 27 of the 35 simulations we looked at also underestimate the heat content. And the ones that get as much heat as the observed, they're really overestimating what's happening, the amount of heat at the surface. So it's happening for the wrong reasons. And so what we wanted to try to understand is, okay, we have this kind of benchmark of there seems to be less heat in general in the models compared to the observations. Is this more related to the amount of sunlight that's getting in at the surface that's local, or more advective processes related to the Pacific water? Okay, and so to look at that, we go back to these temperature profiles. So this is showing from the reanalysis data. Each line is a monthly average. So you have the warmer months showing warmer temperatures. So this is, again, temperature with depth. And we have that first bump at the top from sunlight near surface temperature maximum, and a second bump at depth that's indicative of Pacific water. And here, just as an example, this is showing CESM2, but it turns out most models show the same thing, where you get this seasonal evolution of heat likely from sunlight, but there's no second bump from Pacific water. That seems to be missing. One exception to this rule is EC Earth, which was able to show a Pacific water signature at depth, as well as a near surface temperature maximum, but these were the only ones, and we'll talk more about this later. So talking about bumps is great, but it's good to quantify things. And so to do that, we went through and just looked at a PDF of all the temperature maxima for both the near surface temperature maximum and the Pacific water signatures. So first, talking at the surface, we looked for any indication of a temperature maxima within the winter mixed layer depth range, so something that's seasonal. And we found that in general, almost all the models were able to show this signature in the summer months, consistent with the reanalysis data. By contrast, Pacific water, almost none of the models were able to capture this temperature maxima at depth, apart from EC Earth. So there's a chunk of models over here that seem to get it right, and pretty much all of them are variations on that EC Earth model. Okay, and so that's quantitative, but it is still somewhat useful to know, okay, qualitatively, what are we seeing? And again, looking at CESM2, we're basically seeing this variation seasonally at the surface, followed by a minimum and then warming from Atlantic water, and almost nothing really indicative of a Pacific water inflow that's carrying heat with it, apart from EC Earth. Okay. So that's qualitative. And so the next question we wanted to ask, well, okay, it seems like the Pacific water heat signature from the Pacific water is not really showing up, but we want to get a sense of why, to as much as we possibly can, given that we're just looking at model output. And so we're trying to look at different signatures of possible biases and what it could be related to. So first, thinking about the observations, what we expect is you have warm, salty water from the Pacific going into Bering Strait. And because it's saltier, that is denser and heavier, and so it'll sink down, bringing the warm water in it that subducts below the cool, fresh water in the Canada Basin. So one possibility, as we talked about before, well, we know the surface of the Canada Basin in the models is too salty at the surface. And so if that's the case, then maybe the Pacific water can't subduct below it because it's about the same density and they just kind of mix. Where on the other hand, if it's more of an issue of vertical mixing, perhaps that warm heat gets vertically mixed away at depth well before it can enter into the Canada Basin. And so I'll just note for both of these scenarios, for now, we're just going to assume that there's enough heat that's entered through Bering Strait, and we're just seeing what's happening with the dynamics related to the salinity. Okay, so this is just coming back to that first figure showing temperature with depth for the reanalysis data. CESM2, which is similar to most of the models, and EC Earth, which is this interesting outlier that can show Pacific water. And now we repeat these same figures, but showing salinity with depth. And so what we see is that compared to the reanalysis data, CESM2, as we saw initially, it's much less stratified and saltier. And so that's, again, indicative of perhaps too much vertical mixing, whereas the outlier in EC Earth that was able to show Pacific water heat, it's much more stratified. So perhaps this is saying that in a model where there's weaker vertical stratification, that allows for the heat from the Pacific water to come in. Okay, but another possibility is that the Pacific water never fully subducts, and this is due to the fact that it's unrealistically salty and therefore dense at the surface, so it can't mix in. So to get a sense of if that might be happening, we looked at a few transects starting from the Bering Strait and entering into the Canada Basin. So this is showing the World Ocean Atlas in September on the left and CSM2 on the right. So first, starting with the observations, we see, so we have contours of temperature. So we see it starting warm at low latitudes, and then that heat comes in roughly following the contours of salinity and entering down. Whereas CSM2, you see these strong vertical bands in temperature, indicative of vertical mixing that never really makes it very far north. And now we contrast that with EC Earth, which was much more strongly stratified. And we do see that this heat is able to enter further into the basin compared to CSM2. But once again, there still seems to be a lot of vertical mixing of some sort, or for some reason, that it can't enter into the Arctic basin nearly as much as we see in observations. So it could be two parts here, but process studies would be needed to kind of sort that all out. Okay, I hope I haven't gone too far over. So now I'll just come to our summary slide. So we
You're
looked
good.
at,
You have about 4 minutes left. Sorry.
oh, great. Okay, cool. I meant to do a timer and I forgot. Okay, I'll just quickly summarize and then I'll stop for questions. So we're interested in looking at the upper ocean heat storage in the Canada Basin, and we use CMIP6 models and compared it to reanalysis data, or 5. And we're really interested in understanding how this bias in the salinity stratification might be impacting what's going on. And we saw overall the models tend to show less heat stored in the top 100 meters compared to that reanalysis data. And by just looking at the temperature profiles and looking for bumps at depth, which is indicative of that heat signature from Pacific water, we found that there was a real issue with the model simulating a heat source from the Pacific. And we started to think about, well, is this related to vertical mixing or lateral mixing? And so we looked at vertical profiles of salinity, and we saw that the one model that was able to accurately simulate that heat bump at depth did have a much stronger halocline, more stratification, and likely weaker vertical mixing. And that was able to have heat that was able to enter the Arctic Basin a little bit more realistically than models like CSM2, which had that really strong vertical mixing. And I'll stop there. And my email address is here if you have other questions and want to chat. Thanks.
Thanks, Erica. So I'm looking for questions in the chat and Q&A. I typed one in. I typed one in kind of midway through your talk, and you kind of answered it as you went along. But I'll ask it. I'll ask it again just to make sure I understand. So, like when you looked at the location of all the temperature maxima, you know, for the NSTM and then also for Pacific waters, were they always like well separated features in all these different models? Because it seems like, you know, when you do this broad brush analysis, you can miss things. I think you kind of answered it because you started looking at transects as well, and that really connects the Pacific, connects the Pacific to the Arctic through the Bering Strait. But I don't know if you want to comment on that.
Yeah, no, that's a great question. Thank you. Yeah, because it's really hard in the observations. We're like, okay, this is a normal feature to see at depth, but we know there's a lot of things going on in the model. So just because you don't see that bump doesn't necessarily mean there's no heat coming through. So there's another scenario where maybe that heat's getting there, but it's being seasonally vertically mixed away. And it's not looking like that in these particular transects, but I don't think we're able to rule that out yet. And that would probably take some process studies to actually look and see what's happening to the heat.
Great, thanks. There's another question. Hi, Erica. Array biases. Do you know how large the internal variability is versus the model spread?
Oh, that's a good. And I wonder in which sense does it say about heat or salt or?
No, but I'm guessing it might be temperature. Yeah, just
probably
guessing.
temperature. Yeah, I'm gonna guess. So I would say the model spread is probably going to be bigger than the internal variability. Everything that I've seen in the models, the internal variability is surprisingly small, especially when you get away from the surface. So that'd be my hunch, but I haven't looked at that directly. And if I have, I've forgotten.
Yeah. Something to look at.
Yeah.
Okay, great. All right. Well, thanks very much. So stick around. We might have some more discussion afterwards. Okay. I'm going to move on now to Sylvie. So scheduled on that slide, I showed 16:55, but we're 15 minutes ahead. So Sylvie, please go ahead and share your slides, and I'll give you a warning at after 10 minutes have passed.
Okay.
Go ahead.
So good afternoon. Thanks a lot to be here. The focus is a little bit different. We are going back to the atmosphere numerical weather prediction for the short range. I'm Sylvie Leroyer. I'm research scientist and currently research manager at Meteorological Research Division. And as such, I'm presenting this very highly collaborative work in Meteorological Research Division and CCMIP for ECCC. And I didn't have enough with 12 names, so here are the complete full name of the participants. And clearly, it's a very collaborative work, so it's at the end of the project, it might involve even more people. So just to provide you with a background, so numerical weather prediction is evolving. It was evolving slowly since recently, and the developments were going like piece by piece, and then we are going towards a coupled system where we're trying to resolve the Earth system model in an integrated manner. So we've got improvement in numerical weather prediction method, and with the resolution that is increasing, more atmospheric physics that's being resolved in comparison to parameterization. Then came the advances in land surface modeling, urban modeling, and we are now with multi-layer canopy models. And the surface assimilation system are also evolving. So first, we didn't know the soil moisture, but now the screen level temperature, humidity, but now we have data on soil moisture. So it is evolving also the atmospheric assimilation system. So applications are weather prediction, but also hydrology, environmental modeling. So how can we merge all of this to get proper prediction of the Earth system? So here is the current short range prediction in Canada. So it's called the HRDPS. So the GEM atmospheric model. I try to have an overlook of that. So surface and atmosphere are coupled. So with the GEM atmospheric model coupled with a GEM surface scheme, so that there are actually different tiles representing different landscapes, with notably the ISBA for vegetation. So for the surface scheme, we have a surface data assimilation, and currently at the operation, it's CADAS that is based on the air temperature and humidity at the screen level, without knowing the soil moisture. We have in parallel a development of the land surface modeling, HRD LPS, and the point is that it's offline, it's in 2D, so the same structure, but then it uses forcing from another model, operational model, and it is linked to provide hydrological prediction, but it's not the focus today, and also near surface weather prediction. So so the surface scheme is initialized with the surface data assimilation with CADAS-SAT that is using in particular satellite retrievals of soil moisture. So that is the major change. And this study, actually, we want to use the satellite retrieval for soil moisture and temperature, but still coupled with the atmospheric model. And then it's not the idea is that it takes some steps to go to have the same quality and to have to be able to resolve all the system altogether. So this is the initial performance of the new system that we call MOSA for the presentation versus HRDPS. This is some results we might have some more recent, but we have to stop for the presentation. So some scorecard we compare 1 year evolution, 1 year cycle for different seasons. So the different system, and it turns that the 2D system actually has a good quality of near surface meteorology, better than HRDPS. But then when we coupled everything, for the moment we don't get all the better performance everywhere, all the time. So we highlighted, so we have many sub projects, but we highlighted two important situation that we have to resolve further. So, for example, we have a warm and dry daytime bias in agriculture landscape in the US, Middle East during summer, and also some cold and humid daytime bias in other seasons for the prairies and agriculture landscape. So now we have satellite remote sensing retrieval for soil moisture, and here we compare with the in situ soil moisture, and so they are not assimilated, so it's independent, and it's clearly the game changer in the Earth system modeling. So this is we use the International Soil Moisture Network here, and this is the region that we highlighted the problem in summertime with too warm and too dry. So this is the superficial layer on the top and deeper layer on the bottom, and bias on the left, and root mean square error on the right. So we see that for the root mean square error, we see that it's more stable during the year in comparison to the former system, and much better biases almost all the time. Similar biases for summer, a little bit underestimated here, but at the end it's not so different, but at the end the air temperature is very different. So yeah, so we have to investigate that much closer. So for the fall problem, for the too wet and humid and too cold and humid problem, this is the comparison between the soil moisture for the superficial layer and deeper layer on the left, and on the right the turbulent fluxes at a nearby station. So we see that we have soil moisture that is almost closer to the observation, even a little bit underestimated, but much better than the former system. So, okay, we have a good soil moisture, but then if you look at the turbulent fluxes, the latent heat flow is much overestimated. So this is provide interesting insight of where we can help the system to perform better. So this is for the evaporation, we found that in the region concerned are with a lot of bare and agriculture landscape. So we found, okay, we have this is the surface and vegetation scheme that we have in the new system. For the bare soil, so the dry soils do not evaporate enough, and wet soils evaporate too much in fall. So the factor controlling the links between soil moisture and evaporations are the interesting properties. So we found the fraction of bare ground and vegetation that is evolving through the year, but a lot of uncertainty in that field. Soil texture also is a big parameter that we are working on to have better databases, and also not only the database, but how we translate into information to the SVS model. And then the physical parameterization. So it's we highlighted that we need to revise the parameterization of the links between the soil moisture and the humidity at the surface that is used in input in the Monino-Bukov similarity theory that is used to compute the turbulent fluxes that will be provided to the atmosphere. And the turbulent fluxes themselves might be needed to be revised with a lot of details. So basically, yeah, the surface-atmosphere interaction is a key process to be better understood to continue to improve the system again. So in conclusion, so this is a coordinated effort toward seamless representation of the short-range numerical weather prediction in Canada. So the system is being built on results from previous research and development, but components need to be adapted in a coherent manner for an enhanced short-range high-resolution forecast. Because it's not when we know that we have better soil moisture, but then it's not as easy, as simple when we couple with the atmospheric model. So we need to revise a few parameterization. There is still some challenge to revise the physiographic data, fraction of bare soil, agriculture, etc. I didn't talk here, but we're also exploring data assimilation capabilities to strengthen the representation of surface atmosphere interaction. So at least with increments at the near surface, we can have an idea of what are the errors that we need to resolve. So this is in iterative process. For the atmospheric components, the next steps for the revision, it includes the atmospheric physics scheme interaction between them, because in this system we are going to modernize from the atmospheric physics parameterization from the version 4 to 5. So, but then the different scheme need to be revised to have a proper interaction between them, between clouds and radiation, and their interaction with the surface. For example, the emissivity from the surface that is being revised also, and the feedbacks between surface fluxes and the cloud and radiation physical processes. So we found that this collaborative framework, in order to be able to better resolve the Earth system model, is quite relevant to advance on integrated coupling system, and actually it's serves as an example for other challenges in ocean atmosphere modeling and etc. And just to final comments, so we found that for a long time, it was the quiet revolution of numerical weather prediction with physical modeling, improving step by step. But then it became very complex. Then to couple everything, we found it's very difficult. But we are challenged by the arrival of artificial intelligence, and that's why we need to get as soon as possible state of the art. What can we do as best for the physical modeling? I think it's important. Thank you for your attention. I have a couple of references. So
Thank you. Yeah, I didn't interrupt you. We do have a minute and a half or so left for discussion. Thanks for a nice talk. Well, okay. I always ask, are there any questions? But it's only those of us in the panel who can ask each other questions. And I typed in a question in the Q&A. Which is whether you could just tell me a bit more about how in the MOSA, like the new system, how the soil moisture is initialized. I saw arrows, but I didn't quite understand like what if that's changed going into this new system. It's I think it has, but I wanted to understand that a bit better.
Oh, it is initialized with the CalDAS data assimilation.
Mm-hmm.
Yeah, oops, here.
I see. Okay. So that and CalDAS does okay.
Sorry, there is some delay.
Yeah.
Okay, so yeah, the CalDAS, the version that uses soil moisture from actually from SMAP and CMOS, and also temperature from GOES. These are the current satellite retrieval that we are using. But it can evolve also, but for the moment it's the satellite one. So this is the system, the CalDAS also yeah, there is a reference at the end. So it uses also the offline system internally. So and then so it provides almost true initialization. But then the scheme is through the simulation, the scheme. I think I didn't mention, but the SVS that is replacing ISBA. So this one is making the soil moisture evolving through the RED. So only the initialization is with satellite.
Okay. All right. So thanks for the answer. Just a second here. My timer is going there. So there's a question that's popping up, and I think I can encourage people to add in other questions. What we'll do now is we'll go on to Jason, and then who's kind of continuing this discussion of sort of next generation stuff going on in ECCC systems, and then we can come back to the next question for you, Sylvie. So Jason, why don't you go ahead and share your slide, and then we'll have time for discussion at the end. So I'll start the timer, and I'll give you a warning when 5 minutes are left.
Okay. Can you hear me okay?
I can hear you just fine.
Okay, I am attempting to share my PowerPoint. It's not happening for some reason.
Here we go.
Oh, there we go.
There it
Okay.
is. Yep.
I'm in full screen mode now. All's
You
well.
are. Yeah.
Okay, good. Thank you. Okay, yeah, so I'm a research scientist in the Meteorological Research Division, a colleague of Sylvie. I've been working quite closely for the last several years on grid scale clouds of precipitation parameterization schemes in focusing on numerical weather prediction models, but they're becoming increasingly used in regional climate models and GCMs. So I'm going to presume to give some thoughts on the future of microphysics parameterization in such models. I usually go overboard with talks, so I'm going to start with the conclusion. And the punchlines are that first, bulk microphysics schemes will continue to play roles in models for decades to come, and that convergence around a single community scheme may be advantageous to all towards improving that. So first of all, so this is a depiction of model clouds in a high resolution model. So in models, clouds are represented by a combination of various schemes: deep convection, shallow convection, and so forth. I'm talking exclusively about grid scale condensation schemes, or so-called cloud resolved schemes. As models go to higher resolution, these become more and more relevant. So this is where I'm putting my money. So basically, cloud schemes have three roles in models. They compute optical properties for radiative transfer. They provide feedbacks to the thermodynamics and surface precipitation. So this is a more detailed depiction of the in-cloud microphysical processes that need to be computed. So it's a very complex set of processes, and the details matter to the ultimate those three roles and how that's done. So there are basically three methods for modeling grid scale clouds. One is the so-called bulk approach, in which hydrometeors, or sort of in-cloud water particles, are partitioned into predefined categories like ice crystals, snow, graupel, and so forth. The size distributions are represented by analytic functions, and the microphysical processes basically change the parameters that define the analytic function. Usually it's a gamma function. The next more detailed scheme is so-called bin schemes, or spectral schemes. Liquid particles are now all represented by just liquid, but ice is still typically represented by predefined categories. The difference in bin schemes is the size distributions are discretized into a number of size and or mass bins, and then the parameterization of physical processes just determines the number in each bin. So these are much more detailed in terms of the representation of the size distribution. The new and cool technique is the so-called Lagrangian or particle-based approach, in which individual particles are represented. So it starts off with a single aerosol particle, and then it just evolves in time and space, and the exact location is tracked, and the physical properties evolve. And each particle represents the so-called superparticle, representing a multiplicity of various particles. So in the bottom middle is a a very high resolution large eddy simulation, and the color bars I think represent different trajectories and so forth. So in operational models, or climate models included, everything uses bulk model. Bin schemes and Lagrangian schemes are sort of tools for very high resolution research models. So presumably they are better than bulk models, otherwise why use them? So in terms of looking towards more the models that we're concerned with, the question would be then, I guess, can they be used to train AI models to replace bulk schemes? Possibly, but that would require that they are actually demonstrably superior to bulk schemes in terms of compared to nature, and also actually feasible to be used to train AI models. So start with bin schemes. The standard claim that's made by developers and users of bin microphysics is that they're inherently superior to bulk schemes and should be therefore used to calibrate and improve bulk schemes. On the left is a depiction of some idealized, this is a real case squall line simulation. On the top is observations. On the second, third, and fourth rows are results from 3 different bin schemes. If that statement were true, these things would all look the same, and they would all look like the observations. Problem is that there are inherent problems with bin schemes that are the same with bulk schemes, having to do with predefined categories. Furthermore, there's inherently problematic numerical diffusion. The point of this is that bin schemes are basically will never be used to validate bulk schemes and don't really have any relevance with operational models. That said, bin scheme results can be useful to give guidance in developing the modeling of individual processes. On the other hand, having said that, Lagrangian schemes are really taking over for that. In the bottom left is an example of, don't worry too much if you don't understand what this means, just a bit of eye candy. But the point is that the Lagrangian schemes overcome some inherent weaknesses of bin schemes. The problem is they are extremely expensive, and they're really inherently designed for large eddy simulation models. These are models that run on 100-meter grid spacing or less. And so computational resources simply don't allow large domain simulations to be used for training data sets to train operational models, which means logically we're stuck with bulk schemes. And I think that that's going to be the case for decades to come. But Lagrangian schemes will likely be used to help improve the parameterization of bulk schemes. Okay, so given that we're stuck with bulk schemes, I'm posing the question, what's the best framework to continue to advance our capacity to model microphysics and cloud microphysics and models? We'll go into a little bit more detail. There's basically 2 types of bulk schemes. The one is what I call traditional or category-based schemes, which continue that old sort of the original paradigm of predefining hydrometeor categories into typical categories like rain and snow and so forth. The more modern approach is property-based schemes, which use generic categories, which are sort of undefined, and they predict the properties in time and space. So this is sort of an illustration then of the category-based scheme. So just in terms of the ice phase, so ice particles are sort of partitioned into these predefined categories. But the problem is that the physical properties are continuous in nature, and there's no such thing as conversion between these categories, and so it's inherently problematic. Property-based schemes, on the other hand, as I said, it's not predefined categories. I'm talking entirely ice at the moment. This is a sort of a busy slide for the P3 predicted particle property schemes that was built about 10 years ago. And so if you look at that sort of 3-component hydrometeor thing in the middle, that's sort of in contrast with these predefined categories along the top, those 4. And so because of the details and the prognostic variables and the sort of the type of physical properties that could be computed, The point is that the growth and decay processes can be modeled. So on the left, bottom left, is just sort of a depiction of the various evolution of ice phase microphysics and mixed phase particles. So property schemes can do this much more realistically than category-based schemes. So specifically with regards to the P3 scheme, which, as I said, we originally built about 10 years ago. I'm not going to go into all these details on the left there, but just the point being that this is sort of a flow chart of some major upgrades that we've done over the last several years. So we've been continuing to develop them. This is operational in the HRDPS. It's the official scheme now in the NSSL's exascale climate research global climate model. Oh, I put since 2020X. I forgot to fill in the blank. It's 2021. And just a bit of bragging rights, P3 has also been incorporated into a handful of other different models around the world, from GCMs to LESs. This is just a little bit of eye candy.
Jason, just to let
5 minutes? Okay, perfect. So I'm not going to go into too much detail about this. Again, this is just a bit of eye candy, just a bit of a sampler of some of the developments that we've done. On the top left, there's just to illustrate that the radar reflectivity for this is a squall line, 1 kilometer squall line, has been improved since the operational configuration in the middle in the HRDPS. On the right is some work on winter precipitation types. I won't describe the details there, but the point is that incorporating secondary ice production can improve the prediction of freezing rain and ice pellets. And this was in the HRDPS configuration. On the bottom left is a couple of simulations of hailstorms that paper is just under review now. And on the right is a paper that's also under review, again, looking at the impacts of secondary ice production in tropical deep convection, and which can also be applied to mid-latitudes at coarser resolution. And this has been used to develop a conceptual model for the prediction of this, for the production of high ice water content, which is an aviation hazard. Okay, and just the development continues. This is extending from that flow chart on the top left, where these are some R&D projects that are under preparation, so-called complete triple moment. Those are some idealized hailstorm simulations. Won't go into that. On the far right is just a sample of building in the prognostic aerosols. In that regard, we're catching up to the HER model based on the Thomson-Eidhammer scheme. And I won't mention single category liquid. Prognostic ice habit represents, well, as it suggests, sort of more explicit or prognostic information about the actual shape of ice phase particles, which impacts growth rates. And at that point, on the bottom left, V8, which I'm referring to as Manhattan, our target, is sort of a metaphor for having a microphysics scheme, the bulk microphysics scheme, which is sort of second to none in that it will have the framework that no other scheme will have anything that we're lacking. But beyond that is improving the parameterization of individual microphysical process, and that's going to take a long time based on laboratory measurements, theoretical science, and so forth. And that's the ultimate destination, targeting Berlin. P4, so-called perfectly parameterized physical processes. We will never accomplish that, but the route to getting there is necessary in order to prove models. And just a note on the far right that P3 is going to be implemented into the CAN-ESM. Speeding up here, this is the penultimate slide. What's the best way to move forward then in bulk schemes? There's sort of 3 approaches. One would be to continue to develop predefined category-based schemes and do so independently and competitively. That approach has been what has got us to where we're at, in a sense. It's been useful, and the competition has been friendly competition and beneficial. But as I've indicated, category-based schemes are I think, not. I think they're moving out. So we could secondly use this approach, independent and competitive approach to property-based schemes. There are literally only two that I am aware of that are in existence. In my opinion, it makes some sense to consider collaborating or converging around a single scheme and using that as a community scheme, because the internal parameterized processes, the individual microphysical processes, there's still a lack of physical understanding of how to do this. Working with multiple schemes is, I think, becoming less constructive, less efficient, and I think I'd propose a consideration of working towards on a community scheme, to which, of course, I am advocating the use of P3. So in short, again, my conclusions: bulk schemes are going to be with us for decades to come, and this is regardless of the impacts of AI. AI will change this, but bulk schemes will continue to be quite useful, quite needed in operational models. And I propose convergence towards using a single scheme. Okay, thank you.
All right, thanks, Jason. So you're right at time, and now my timer's gone off to prove it. So which is cool, because we actually do have. Hold on, let me see. Am I misrepresenting where we are in this session? I felt like we had an extra slot. I think it goes till 5:30 our session, so let's assume it does. We have a bit more time. So I just like, okay, I asked a question, and I think we're getting similar questions. Let me just phrase it in terms of somebody else. Can the P3 scheme be applied to regional or global scale models, say 10 kilometers or more? Is the plan to use P3 on the GDPS?
Well, yes, sort of. It depends who you ask. I am not in charge of the GDPS. There is a project that has been ongoing to make adaptations of P3 for that system. It requires a subgrid cloud fraction parameterization, and we have a very simple one in place. There have been sort of various teething problems and so forth. It certainly could be. I think that it in a sense doesn't make sense to have it in an LES, a kilometer scale model, and a GCM, but then have something intermediate in between. So yes, but I'm not in charge of that decision.
Right. Okay. So I just wanted to jump back a bit and just there's a question that was upvoted. So I'm going to ask it. I think it belongs to, it goes with Sylvie, but honestly, I think it could be applied to your talk as well, because it's kind of about calibration and tuning. Since not all models are modified, so let's say for Sylvie, since not all models are modified at the same time in the iterative upgrades, is tuning always done, or is there any intermodels interface that modulates communication between models? I can cut and paste that question into our chat here in the panel to make sure that that's understood. So Sylvie, do you catch that question?
Yeah. Well, yeah, that's the key point. Yeah, it's an iterative process. We cannot change everything at the same time. So
I think it's a bit about the software development though as well, like an ability for models to sort of, as they're being changed and you're swapping pieces in and out. I'm not sure. I was wondering if Clint asked this question, or I'm not sure who did. But if there's a way, if there's like, I don't want to misinterpret the question, but intermodels interface, right? Like that's kind of the key thing. Is I think the interface is talking about using modern computing techniques, software techniques to sort of test out and get different models talking to each other, even when they're not completely calibrated or tuned.
Yeah. Well, yeah, we do. I'm not sure I understand. We try to have a setup. That's why it's very difficult to have to work really close all together and build an experiment after another and select. I identify which process is okay, which is not, and continue with that. But yeah, it's I don't know what. Yeah, I'm not sure. I
Yeah.
get exactly what I can
I
answer.
think
But
part of it too is that I think there's like this. Well, maybe I'm just talking about what I'm interested in. Or I've heard about that this idea that you can start to do these tuning and model development when you start using more machine learning and AI, kind of more online coupling, and so you're estimating parameters. You're also sort of working on your parameterizations, and everything's going on all at the same time, rather than sort of step by step. Which so the online learning in an interactive setting, and has like there's more and more software, I think, or more development oriented that way. So that might be what that question is alluding to. I'm not sure. Okay, let me keep going.
Can I just make one comment on
yeah,
that, Paul?
for sure, yeah.
This I don't think this is entirely what the question is about, but it's sort of related.
Is
that I'm sort of thinking of improvements within a system, but without, and then having to balance the system with itself, the various parameterizations. That's a complex problem, and one of the things is that a numerical model is basically a set of compensating errors and approximations. And so if you take one scheme, for example, and you improve it, in other words, you reduce some of the errors, you throw things off balance, and the total solution makes it worse. That's not because you've done anything wrong with that particular process. So then it goes back to trying to figure out why and rebalancing everything. So I think that's a sort of it's the same idea of sort of balancing modeling systems with and the interface and so forth.
yeah, exactly. If I can take the example with hydrology, the soil moisture. So before the idea that we didn't know soil moisture, but we estimated it with the near surface air temperature. So yeah, so then it was working, but for the wrong reason. We didn't have the good soil moisture. So then now we have the good soil moisture, but then we can highlight some limitation of some parameterization that we didn't see before. So it's not this. So what is it? It's not exactly turning, but just we now see the problem that we didn't see before. But it's yeah. The way to do that, there's no. It's yeah. It's step by step.
Yeah. Okay. So there was a question for Jason. Do you think that the experimental and field work is keeping up with the need, the needs for validating microphysical schemes and so many different areas of application? And do you think there's enough work on like standard benchmarks for AI related work as well?
Yeah, well, for the first one, I think I could say no. Well, let me rephrase. It's an important question. It's an important part. Most physics parameterizations in numerical models are subgrid scale problems.
Yeah.
It's a sort of computational resource problem. The physics is understood. It's just a matter of limitations of grid spacing and so forth. With representing clouds and cloud microphysical processes, it's not just subgrid scale. It's a parameterization squared problem because you've got clouds and then you've got particles. But the other thing is that we lack a complete understanding of the physical processes, and so and a lot of these it's not just esoteric and sort of theoretically interesting. It impacts the solution. You can't parameterize something if you don't understand the underlying physics. So I showed a couple of results with secondary ice production, and we definitely show that it matters how you do it. So secondary ice production is when you have existing ice and one or other mechanisms cause smaller ice to form off of that. So the ice crystals become more numerous. And that requires field work and it requires laboratory observations. So there was a review article that was written in the State of the Art in Cloud Microphysics for the 100th anniversary of James. And one of the conclusions, several of the conclusions were, what's needed to advance microphysics is not better microphysics schemes, it's better lab work and observations and verification techniques, because we don't need to be able to characterize the errors. I can't remember,
Well, the other question was, what's one I pinned down, I wrote down, but I've been asking a couple of speakers about just the development of, so part of the AI world is, is creating benchmarks that people with less subject matter expertise than, people like you guys have been trained and done work in this in your areas for a long time. You create benchmarks that are sort of objective, that people can use for calculations and applying, up to date techniques towards. I was wondering if I've heard a little bit about in your domain about those kind of benchmarks, but I was wondering if what you think of them, and whether there's anything that's, I don't know, accepted enough, either case studies or particular field campaigns or lab tests that would qualify to be a kind of published benchmark for this work.
Yeah, I made the point about that 3D models using bin schemes are not an option, because bin schemes are not.
They're not. Yeah, that's a
Yeah.
counter. Yeah, I believe that. Right? You made that case pretty clear, right? So
yeah. So, and I think 3D models using Lagrangian schemes are just astronomically too expensive. So I think we're stuck with 3D. Like large scale, like for NWB training sets using bulk schemes. So the question then is your model, high resolution model, good enough? And I think you just need to, it needs to be sufficiently validated to be close enough to high resolution observational data set using radar and high resolution satellite observations and so forth.
Right.
I think that's the best. That's to me the best thing I can think of.
So if I was to put you in a cage and say, okay, now pick the best, what would you say, or like if 3 or 4, could you identify a handful of radar observational data sets or compilations or something that people could appeal to? You don't have to answer this, but I'm just thinking about that, like something that you could say, okay, this is the go-to data set. Of course, might not be, but you or the ones you use, right, in your practice.
Yeah. To be determined. I'll plead the fifth on that one.
Okay, that's fine. That's fine. No worries. All right, let me do a quick scan here. I think we've gone through all the questions that were posted. But I'm really glad to hear this whole range of talks in this last session. Is a little kind of a variety of topics, but just shows me that there's a lot of collaborative Earth system modeling going on in Canada. There's if you look at the MRD, Environment and Climate Change Canada's Meteorological Research Division, it's like a very large team, right? And it's an international collaboration as well. So, and then you have the whole CanESM effort, which also has like a network as well. So I think it shows you the size of the teams that need to be involved to make progress on these problems, but the good individual work you're doing too. So thanks everyone for some great presentations, and please feel free to keep in touch and let us know, just send some feedback, what you think of having this collaborative Earth system modeling session. And my plan is to keep proposing it each year, and see, as long as people submit papers, we'll just keep doing it. So thanks a lot, and have a good rest of your day. Bye.
Thanks, Paul. Bye.
Thank you. Bye.